Okay, we'll go for the second talk in the afternoon. So thank you very much, Bruno, for being here. The floor is yours.
Thanks, and let me also thank all the organizers for this very nice workshop and for the opportunity to speak here. And yes, today I'm going to talk about ADS from higher dimensions, and this is going to be based on some published work and some collaborators, among which Alessandro, which is here, and some work in progress. So let's start. I'm going to be brief on the motivations. We had many, with few reviews already, and the problem is that we are working in higher dimensions. We come from the top down, and we have to deal with the extra dimensions. And in particular, we want to understand how to describe four-dimensional physics if we start with more than 4 dimensions, and we also want to describe realistic four-dimensional physics, which means many things. And in particular, here we mean to see if we can get de Sitter from higher dimensions. So four-dimensional de Sitter. We have heard about many approaches and constraints and so on. And what I will try to do in this talk is to get these constraints and directly from the equations of motion of generic high-dimensional theories of gravity, and discuss how we can evade those constraints and propose some possible solutions to some of these challenges. So let's start. We are working with the higher dimensional theory of gravity. So we assume that we have some theory that at low energies reduces just to Einstein-Hilbert in given a large D number, large meaning 10 or 11, for example, number of dimensions with some matter content specified by the theory. And we look for four-dimensional physics. So the first thing we do is to, for example, look for vacua, meaning that space-time where we have a four-dimensional vacuum, some internal space, and possibly some warp factor. And if we look for these solutions, then the natural thing to do is to just write down the generic equation of motion for this theory and plug the answers. If we do that, we get some set of equations. We get an equations along the space-time and some internal equation, some sort of Einstein equations in the internal space. And these equations specify, if you solve them, you find a vacuum. But to have really four-dimensional physics, we also want to know something about the fluctuations around the vacuum. What's the particle spectrum around the vacuum? And this means, for example, looking at the Kaluza-Klein modes as fluctuation around the compactification around the vacuum. So in general, it's hard to find the Kaluza-Klein modes for general spins, but at least for the spin 2 fields, there is a universal formula that gives the masses of the Kaluza-Klein modes. And is given by this simple operator that only depends on the warping other than the geometry. And so, if you're interested in dealing four-dimensional physics, it means that we want to solve these equations, actually the 3 of them simultaneously. We want to know what kind of vacuum we have and what kind of a spectrum fluctuation we have around the vacuum. So we need to solve the equations for the vacuum and also be able to say something about the masses or particular eigenvalues of this operator. Now, also we want to find constraints that apply to all solutions without going case by case. And well, we already heard about this in the previous talk. There is a very nice constraint you can obtain directly from the vacuum equation, this one. If you assume that the internal space is smooth and without boundary, you can integrate this equation and you get a constraint on the sign of the cosmological constant. And in particular, what Maldacena and Nunez showed that, so you see you have here an integral of certain trace of the stress energy tensor, and this determines the sign of the cosmological constant. And what Maldacena and Nunez showed is that if you only consider fluxes or localized objects such as D-branes, well, then this integral has a definite sign and you're forced to have a negative cosmological constant. But you can consider more general sources where this is not true, and you're going to see an example. And also this is violated also for oriented for planes, as has been already discussed. Now, we would like to do something for the other 2 equations, something similar. For example, can we obtain general constraints? And well, the situation is harder because the equation that we get in the internal space is not a single equation, it's a tensor. This equation is a tensor. And also we have these derivatives of the warping, which we don't know much about. And however, interestingly, this particular combination of curvature and derivatives of the warping has been already studied by mathematicians in the context of optimal transport theory. And what I think is interesting is that what the mathematician showed is that if you're able to say something about this particular tensor, you are able to control the spectrum of this operator. Meaning that if you know something about this Ricci curvature corrected with this warping, that has a name, it's called sometimes effective or synthetic Ricci curvature with a certain effective dimension, then if you control this tensor, you can control the spectrum of this operator. And I don't have much time to get into the details, but I just want to give you some example of what kind of results you can obtain. So the equation of motion has this form, this effective Ricci tensor equal to the cosmological constant plus a certain combination of stress energy tensors. And for example, you can first ask whether you can bound these and have some general properties of these stress energy tensors. And what we found with Alessandro is that indeed you can. And for example, if you only consider again just fluxes or classical sources with positive tension, such as the branes, then this combination of stress energy tensor is non-negative. And this means that you can bound this effective Ricci tensor just in terms of the cosmological constant. And we gave a name to this condition, we call it reduced energy condition. It's slightly different than the Malassina-Nunez because here, or particularly slightly different than the strong energy condition because, for example, this applies also to the Romance mass. And so this is a case in which you, if you are in this situation, you can bound this effective Ricci tensor just in terms of the cosmological constant. And here, then we can ask, okay, can we use this to find theorems on the ratio of the spectrum of the Kaluza, on the ratio among the Kaluza-Klein modes and the cosmological constant? And the answer is yes. I'm going to flash quickly some results here. You can just go to the mathematician and say, now I have a bound on this Ricci, effective Ricci tensor. What can you tell me about the spectrum of this warp Laplacian? And what we find, for example, is that there are lower bounds on the Kaluza-Klein spectrum in terms of some geometric quantities, such as the diameters or geometric quantity known as Chigger constant. And you can use that, for example, to prove that certain solutions have scale separation if you're able to estimate these other geometric quantities. And here you don't have to make any assumption on whether the Kaluza-Klein scale is related to the volume or the curvature, as Thomas introduced yesterday, because here we are already bounding directly the operator that gives the masses of the Kaluza-Klein modes. And or you can try to go the other way around. You can ask, can I disprove separation of scales in certain settings, meaning that you would like to find a lower bound on these on the masses of the Kaluza-Klein in terms of the an upper bound in terms of the cosmological constant, and you can do, but so far the theorems that we found are not enough to exclude separation of scale, even when you just assume these reduced energy conditions. So we don't know so far whether, because in general you can exclude the separation of scales. But it's true that when you have these reduced energy conditions, so just say classical or positive energy contribution, you get some constraint. So you can ask, what happens if I try to evade these energy conditions? And I want to argue that you have much more flexibility and to find interesting quantifications, because when you evade this assumption of positive energy, then you can stabilize flat or negatively curved internal manifolds. And those have a much richer structure that allows to find, I will say, interesting physics. And a way to organize this discussion is in terms of the potential, the effective potential for a generic quantification. For example, when you have, in particular, when you have warping, this was worked out by Douglas, and when he showed that if you take this potential where you have a curvature term corrected by the warping, then finding minimum of this potential is completely equivalent to solving the higher dimensional equations of motion, but gives a nice intuition on what kind of situations you can have. For example, this is a potential for all the degrees of freedom, say all the internal metric degrees of freedom. But if you study it in terms of the volume, for example, the first thing you can ask is how can I stabilize the volume? Well, you can look at the potential, you see that the curvature, a positive curvature corresponds to a negative potential, and the positive energy, in the sense of the energy condition we discussed before, means a positive term in the potential here. And then you see that, well, you see immediately how you obtain Malassina-Nunez, because if you have only positive sources here, the only way to find a minimum is with positive curvature, and the minimum is going to be ADS. And this is pictorial representation of Maltesian limits. But then, if you allow for energy sources with a different sign, you can have more general situations. For example, you can have a case where you don't have any internal curvature and try to balance the two different signs of energy sources. And this will mean a flat internal space where you, for example, can have an ADS minimum of this kind, and we're going to see an example soon. Or if you start with this situation, then you can try to add negative curvature, which will contribute positively to the potential, and then you hope to find a situation like this, where you have a minimum which is with a positive cosmological constant. And the motivation to that is that if you can stabilize flat or negative curvature, then you have much more freedom and you can exploit more interesting geometric properties. And we're going to see the details of it in a moment. And needless to say that there are many ways in which you can try to discuss to find sitter or other sort of ADS. We've seen many examples. But let me now just focus on one possibility to get this negative energy term, which is in the form of Casimir energies. So when you have a compact internal space, you can ask whether the boundary conditions that you impose on your fields, whether they generate some sort of 0-point energy in the internal space. And they do, for example, if you are able to break supersymmetry, you generically will expect some 0-point energy. And if you have some cycles, for example, in internal space, you can do that by imposing, for example, antiperiodic boundary conditions for fermions. Those break supersymmetry and generate a 0-point energy that you can use as negative energy sources in the equations of motion. So the idea here is that you assume you have a certain geometry, a certain topology, you compute what are these kind of quantum effects you can generate, and then try to solve the equation of motion semi-classically, making sure that this is consistent, so that the solution, the geometry you use to compute the quantum effect is really a solution of the equation of motion in that geometry when you added that term to the stress energy tensor. And let's see, for example, a very simple example. You can consider M theory compactified on a 7 torus and imposing antiperiodic boundary conditions for fermions there on the torus, and also adding some flux, homogeneous flux in the internal space. And what you get is a potential of this form. So we'll have the negative energy Casimir term here, and the curvature, and the flux term of the potential. So you expect anti-de Sitter minimum, and indeed you can do the computation explicitly for a torus. This is simple. You can write, you can solve all the equations of motion theory in this case, or particular 11-dimensional supergravity, and you find ADS minimum, which is also interesting because it's scale separated. You can compute the ratio of the Kaluza-Klein modes to the cosmological constant in this simple example. You find that indeed you have an arbitrary separation of the internal and the ADS scale, and without needing for the torus to be sub-Planckian. So you can also have control of the other corrections. This is a scale separated ADS vacuum that you get with the Casimir energies, and it has some properties such as it's unstable. For example, we check that it has it allows for nucleation of a bubble of M2. There is a question. Yeah. Well, the torus is homogeneous. Here I'm assuming that there are the torus is just a flat torus without any dependence on the point here. So the only quantity here is the overall size. Yes, it is spread over. The torus is homogeneous and isotropic. There cannot be any dependence here. I'm not allowing for generic moduli of the torus here. And this is just, I'm looking at this configuration. If you are moving away from that, yes, you will generate anisotropies in the Casimir energy.
Is this related to this dimension?
Well, it's related in the sense that here you can, thanks to the combination of these two effects, you can stabilize an ADS minimum without needing curvature. In this sense, it's related. And then with the flat manifold, you have a bit more. You have a decoupling between the curvature scale, which is 0, and the length scales, and that's what's doing the trick here. Mhm. Well, small, I mean, all right, so as I said, everything has to be self-consistent. So you assume that you have a circle of a certain size, and the contribution will go like the size to the minus d, the contribution to the Casimir energy. That's you can compute. And but then indeed you need to make sure that it's self-consistent. So you want to plug in the equation of motion and check what is the circle size that you get to solving the M-theory equations of motion. So you might say, okay, regardless of the size of the circle, you can, in general, you have this formula. But you want it to be strong enough that it has to compete with the classical effect. And this is a question of what the equation of motion are telling you. So you plug in the equation of motion and check when you stabilize, what's the size of the torus. So you would like to be able to do that without needing a tiny torus such that you lose control. Yeah. Or no, that's our question. We don't know what these things decays to. The time scale here, I will say. I mean, it's a non-perturbative instability, and I will say yes, probably is the Planck time. The point is that people don't usually care much about if it's so if it's already non-perturbative unstable. There is this argument that for an observer at the boundary is going to be killed immediately. So we didn't pay much attention to that, but it's a good question. Okay, so if you have ADS in this way, then you can ask, okay, can I add curvature, negative curvature, and by keeping the same set of ingredients, hopefully finding a potential with 3 terms and a de Sitter minimum. And so to see if that's possible, let's briefly discuss the properties of negative curvature. And so the prototypical example is are hyperbolic manifolds. So hyperbolic manifolds are manifolds that you obtain starting from, for example, hyperbolic space in your favorite model of hyperbolic space, and prescribing a certain way to get a finite volume manifold in hyperbolic space. There are various ways to do that, quotienting with respect to some isometry, or equivalently, like a way that I like to describe it is that you have to choose certain polytopes in the hyperbolic space and prescribe some way to glue the faces of the polytopes, identify them, similarly to how to get a torus from a square in Euclidean space. And there are very explicit ways to do that. In particular, there is this recent nice paper that they show how to do it just with right-angled polytopes. So if you do this first, you get a manifold which is finite volume and hyperbolic. And this manifold, interesting, has hyperbolic manifold generically have a certain region which are called cusps, where a cusp is a region where you have certain transverse torus that is shrinking to 0 size very slowly. And hyperbolic manifold generically have many of these cusps. These are interesting for our purposes because this is where you can hope to generate enough Casimir energy to compete with the other effects if you want to use this in a compactification. But we don't literally want a cusp because a cusp is going to shrink to 0 size, and once it gets below a certain size, we might lose control of what's happening. But luckily, there is a way out to this, which is that we can cap off the cusp, so we can truncate the cusp, ending the geometry in a smooth way. And this has been shown, has been proven in this paper by Anderson, that you can do it in generic dimension, and this is sometimes called Anderson filling, which is a way in which you take any cusp or any cusp that you want of the hyperbolic manifold, and you truncate it by shrinking it smoothly at a certain point, and you have freedom to tune the final size of the remaining torus. And this gives a lot of freedom to tune the length of these cycles and the amount of Casimir you can generate, because you can do this procedure for all the cusps of the torus independently. Sorry, of the hyperbolic manifold independently. And after you do this procedure, you get a manifold which is Einstein. So not hyperbolic anymore in general, but is Einstein with negative curvature, with tunable sizes of these cusps. And another important property of this manifold that make them interesting for compactification is that they are rigid, meaning that once you specify the overall volume, this manifold don't have any modulus. Like they don't have moduli hyperbolic manifolds, or even these Einstein manifolds that you get after doing the filling. And this makes them interesting to try to do compactification, because it makes the problem of moduli stabilization much easier. So these are the properties of this manifold. Let's see if we can use them to find the sitter. So let's assume we are in the same setting as before, M theory, now with the internal space being these Einstein spaces. And let's see what the potential. Well, the potential has three terms, and we'll have this curvature this warping corrected curvature term, the Casimir term, and a flux term. And the first thing we have to do is to see how to stabilize the volume. And interesting, they scale in this way, with the Casimir term being the negative one and sitting in the middle, such that the shape of the potential is this one. So there is hope to find indeed that the sitter minimum in this configuration. And what we do in the paper is to argue that indeed you have a de Sitter minimum if you are able to do a certain tuning, and the tuning being that you need to be able to tune the magnitude of this first term, the warping corrected curvature, and you need this to be positive, so that you start with a positive term here, but very small. If you can tune this, we argue that then you are in a regime in which you can have the competition of the three terms with a positive minimum. And so how to do this tuning? Well, what I'm saying is that you need to tune a certain integrated quantity, and you have a lot of freedom to do that in these manifolds, because you can, as I said, when you construct them, you can choose the size of all the cusps independently, and by this you have a lot of freedom in tuning the amount of Casimir energy that you have, and you also have freedom to tune the flux by choosing the flux integer. So by combining these effects together, we argue that you have a potential with this shape with a de Sitter minimum. And we can try to do another step. We can try to see if we can solve all the equations of motion on these manifolds. And in particular, this is in general a hard problem, means solving all the Einstein PDEs in this non-trivial manifold. But we can start looking for simplification. One is that most of the action is happening in the cusps, and in the cusp the geometry is actually simple in the sense that it depends mostly only on the coordinate along the cusp. So you can reduce the problem to just to an ODE problem, and there you can solve all the equations of motion completely. So here we are looking at this is an answer for what's going on in the cusp, and we try to solve all the equations of motion of 11-dimensional supergravity, so including the back reaction of the Casimir. And you can do that explicitly, and you find indeed a smooth solution with the properties similar to the Anderson field metric. So there is a cycle that is shrinking smoothly, another n-2, so 5-dimensional torus here getting up to a small size, which is enough for it to compete for the Casimir that you build here to compete with the classical term. And on this solution, you can then for example, check the analytic estimate that I described briefly in the previous slide, and we find agreement with what you can predict from the analytic analysis. And in particular, these are solutions of the full back reacted equation of motion that are constructed in a large part of the manifold, because these cusps actually compose most of the volume of the manifold. And so the idea is that for each of these cusps, you have one of these solutions. This is how the geometry is behaving in all of them. And then we can ask, okay, can we find a global solution, meaning that we can ask how does the geometry look like when we combine all these cusps together, these back-reacted cusps together. And we argue in the paper that there is an obstruction, and and you have enough freedom to do this gluing. And to do it explicitly, let's first do a step back and see what happens in the case where there is no Casimir, just flux, and we are just studying the geometric problem. And for example, I told you that you can start with hyperbolic manifolds and you can fill the cusps so that they get up to you get some smooth manifold with the cusps of a tunable size. And Anderson proved that, and the way he proved that was similar to what we are describing. He constructed a solution in the cusp, a solution only depending on a single variable, And then he argues, and the solution is something we know, is a Euclidean ADS black hole, where the circle that is shrinking is just the Euclidean time. And this is negatively curved and has this property. And so what Anderson proved is that you can glue all this together. So he proves that you have all the solution in the cusp, and then you can glue them together such that you get a metric on the overall manifold, which is now Einstein. And it will be complicated in the sense that it will depend on all the coordinates, but he proved that it exists and is somewhat close to this cusp metric. And here we are, for the full de Sitter solution, we are in a similar situation in the sense that we have the back reactor solution in all the cusps. We argue that they can be glued. We don't have a mathematical proof that this can be glued, but we have some estimates that the situation should be similar to the purely geometric case. But already in the purely geometric case, even though it's proven to exist, it's an open problem to construct it numerically. Even forget about de Sitter and Casimir, just construct the metric that Anderson proved to exist. It's an open problem in hyperbolic geometry. And here we're trying to do something similar, but gluing the back reacted cusp with Casimir and so on. And we are trying various approaches to that. One is to use some of the tools that Jim introduced today. So we are trying to use some machine learning methods to do the following. We have the solutions in the cusps, and the only thing that we have to do is to glue them together. And when we glue them, we expect to have some small modification of the original solution that adds some gradients in, say, in the angular direction. And in the overlap, though, they have to solve the Einstein equation, or in particular the equation for a compactification, and the overlap should be consistent. And you can try to do with this method. We use some neural network ansatz to parameterize the metric in the different regions, and then we try to glue together in this way. And while doing that for Casimir, it's a complicated problem, but you can, as a first step, you can try to just solve the geometric problem. And this is something we started doing. We have some very preliminary results in the three-dimensional case, and we would like to scale it up and then add Casimir. This is, let me just finish. And this is one way. And you can also try to do something more analytic. Can we do an Anderson-like proof of the gluing of our cusps? It's a bit more complicated than the purely geometric problem, but I don't see an obstruction to that. And with these, I think I'm done. Let me thank you all for that.
Okay, thank you, Bruno, for a nice talk. I think there was already a question just now.
What's the y-axis on your plot? It's some sort of loss, but I don't see what.
Yes,
What does it depend on?
The loss here. So this is a very simple example. It's not the case where we glue all the cusps. Here we're just trying to fill one single cusp by minimizing the Ricci. So here is the purely geometric problem. So we try to solve Ricci equal to minus central constant.
Just the loss is Ricci, basically.
The loss is Ricci. So it is required to implement, so to do the Ricci in a differentiable way, as you described, and then use the loss. The situation compared to the Calabi-Yau is it has some simplification. Well, it is more complex in the sense that you cannot use the complex geometry. So here you are solving directly the Einstein TVs. Some simplification comes from the fact that we already know an approximate solution. Like as in the Anderson proof, we have a solution which is almost solving the equations of motion almost everywhere, and we predict that there is just a small modification of that. Yeah. So what we did here was to first retrain the network on the approximate solution that we know analytically, and then just ask the network just to perturb that slightly to solve the Einstein equation everywhere. So we have a starting point which is almost a solution of the problem. That's a difference from the Calabi-Yau case.
I see. So, yeah, but then given the neural network result, if you don't regress all the way to zero, do you have in mind to hopefully prove that that also is near some actual solution?
Yes, so that's the goal. Here, for example, in the purely geometric case, we have a proof that exists, and that is close to the original one.
Okay. So, yeah, so I can cite a reference for you later of something in the PDE literature that's analogous, where they actually take the neural network result and prove that in some local neighborhood there's an actual solution. So it could be very useful for you, those techniques.
Yeah,
thanks.
Thanks for the talk. Maybe it's just a lack of intuition. Like you have these cusps, and then you can decide at what volume or length I will cut and I will glue, right?
Yes.
Does this parameter, this length, become dynamical in the low energy effective action when I put the theory, or is a free parameter without dynamics?
So great. So this parameter, so as I told you, these manifolds are rigid. So the fact that you have these parameters might seem in clash with the fact that you shouldn't have moduli, but this parameter is discrete. So it's something that basically you are not free to tune it. So you're free to tune it, but
Non-continuously.
So there is the various manifolds are not connected in a sense that you will have some mass gap to go from one to the other.
Okay, thank you.
That's why they are rigid, even though you have this freedom. And,
Okay, would you then expect that actually they are dynamical, just very massive?
yes, I don't see why you cannot have a transition between various.
Okay,
things, but, yeah.
Thanks.
So I guess you asked one of my questions. So the second question, I don't know if it's naive, but how do I see standard model like physics in this kind of
That's a good
spaces?
question. We need to look at that. I suspect that you can add some M5 brains or intersections of those and try to get.
But then I would have to understand some kind of singularity structure in
I
these
guess so.
manifolds.
Yes, that's a good question. We didn't look at it yet, but.
But is it known? Like people.
Well, is it known, is it known here? Well, I don't know, but in general, that you can use Occident theory brains on singularity or perception and so on, yes. But whether and what you can do here, still something to do.
Okay.
I don't know. But of course, it's important to want to have any kind of realistic cases.
Yeah, Nicola?
Yeah, this is partially related to the last question. Do you expect that in the point in which you realize the gluings, there should be some object?
I expect this move to be, this gluing to be moved.
So you don't have even jumps in derivatives or no?
I mean, no. I expect to be able to find a smooth So, and they, actually, this, for example, this is how Anderson proved that you can do these constructions. That you first glue the cusps with a certain, say, a certain kink in the way they are glued. And but then he proved that a smooth one exists very close to that, which is Einstein. And I expect something similar to be
Thanks.
Okay, yeah, we have time for one more.
In the plot, you have various spikes. What's going on?
I don't know. Well, this is not very unusual actually. So it's typical of some, when the loss is going down.
No, I know. I see some wiggle everywhere, but there's giant spikes in some places. Did something extra happen there?
Not that I know. This was basically just to show if at least the method made sense and the loss was going down to the but I guess there are various to be handled. So maybe there might be some better architecture that it can be is optimized that here. But if you've seen, say, the curves for training transformers, then you see something which is much greater than that, and the end result is
Right?
Do I understand correctly that the Casimir plays the same role as the orientifold? Do I understand correctly the Casimir plays the same role as the orientifold would?
Yes, it gives this negative energy to
Yeah. And then, as Thomas asked, also in this hyperbolic case, it's just a constant contribution. It's not point dependent.
Here,
Yeah.
no, that's why the situation is a bit harder, because here this is not a torus. It's not a global torus. It has some regions where there is this torus, but its size is shrinking smoothly, but its size is changing. So that's why the geometry is a bit more complicated. It's not now it's not isotropic anymore. You need to consider how locally the carbon is generated, and this is what's generating a non-trivial work factor. And for example, you can see it explicitly in these solutions. These are solutions where the Casimir is probably taken into account in the sense that depends on the position along this torus direction, which depends on the size of the torus. And this is why you have a work factor which is constant. But for example, here you can just solve the set of and see what you get.
Thank you.
Okay, and I think we're out of time. Either way, we'll have a discussion on the city later on. So let's thank Bruno again.